Our universe is filled with mysteries, but one of the greatest is something we can't see, touch, or directly detect: dark matter. It's everywhere, making up most of the universe's mass, yet we don't know what it is. What if everything we thought we knew about physics is incomplete? In this video, we'll explore what dark matter is, why scientists are hunting for it, and how it could change our understanding of reality. Imagine an invisible force holding galaxies together, bending light, and shaping the very fabric of the cosmos. Scientists are searching for dark matter with underground detectors, particle accelerators, and space telescopes. Some believe it's made of exotic particles, while others think it might be something even stranger. But if we discover what dark matter truly is, it could unlock an entirely new realm of physics. So, what do we really know? Let's find out. In the early 20th century, astronomers noticed something strange. Galaxies were rotating too fast, so fast that they should be flying apart. But they weren't. Something invisible was holding them together. This was the first clue that there was unseen mass in the universe. Dark matter doesn't emit, absorb, or reflect light. We can't see it, but we know it's there because of its gravitational effects. Without it, galaxies wouldn't exist in their current form. Scientists estimate that dark matter makes up about 27% of the universe, while ordinary matter, the stars, planets, and everything we see, makes up just 5%. The rest? That's dark energy, another mystery entirely. So, if dark matter is real, what is it made of? The leading theory suggests it consists of weakly interacting massive particles, or WIMPs, hypothetical particles that rarely interact with normal matter. Other theories propose axions, ultralight particles that could explain dark matter's presence in the universe. But there's also a possibility that Einstein's laws of gravity might need a revision. Could dark matter be a sign that we don't fully understand the fundamental forces of nature? Since dark matter doesn't interact with light or electromagnetic forces, scientists must rely on indirect methods to detect it. Over the years, researchers have developed three main approaches to uncover its presence. 1. Gravitational lensing, bending light with dark matter. One of the most striking pieces of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. When light from a distant galaxy passes through a massive object, such as a galaxy cluster, the gravitational field distorts and bends the light, much like a magnifying glass. Astronomers have observed cases where light bends far more than expected based on the visible mass alone. This suggests that there is an additional invisible mass, dark matter, enhancing the gravitational effect. Scientists use these lensing distortions to create maps of where dark matter is located in the universe, revealing massive halos of invisible material around galaxies. 2. Direct detection, searching for dark matter in underground laboratories. If dark matter is made of weakly interacting massive particles, WIMPs, it should occasionally collide with atoms, albeit extremely rarely. To detect these rare interactions, scientists build deep underground laboratories where shielding from cosmic rays reduces background noise. One such facility is the xenon experiment in Italy, which uses a tank filled with ultra-pure liquid xenon. If a dark matter particle collides with a xenon atom, it produces a faint flash of light that can be detected. So far, no conclusive dark matter interactions have been observed, but each new generation of experiments gets closer to the sensitivity required to make a breakthrough. 3. Particle accelerators, creating dark matter in the lab. The Large Hadron Collider, LHC, at CERN, is smashing protons together at nearly the speed of light, searching for signs of dark matter. The idea is that in high-energy collisions, dark matter particles might be produced and escape detection, leaving a missing energy signature in the data. Although the LHC has not yet discovered dark matter, it has provided critical insights into the universe's fundamental particles. Future particle colliders, such as the proposed Future Circular Collider, FCC, could offer even greater chances of uncovering dark matter's secrets. Despite decades of searching, dark matter remains elusive. Could we be looking in the wrong place? Or is a paradigm shift in physics on the horizon? Despite its invisible nature, scientists have formulated several compelling theories about what dark matter could be. The leading candidates range from exotic, undiscovered particles to entirely new physics that challenge our understanding of the universe. Let's explore the top contenders. 1. WIMPs, weakly interacting massive particles. The classic candidate. For decades, WIMPs have been the frontrunners in the search for dark matter. These hypothetical particles are thought to be heavy, yet barely interact with ordinary matter, making them extremely difficult to detect. The idea of WIMPs fits well with a concept known as the WIMP miracle, a theoretical framework suggesting that these particles could have naturally formed in the right abundance during the early universe. However, despite massive underground detectors like Xenont and Lux Zeppelin searching for WIMPs, no definitive evidence has been found, leading some physicists to question whether they exist at all. 2 axions, ghostly subatomic particles. Axions are another intriguing candidate for dark matter. Unlike WIMPs, axions are expected to be incredibly light, trillions of times lighter than an electron. These particles, if they exist, could subtly interact with magnetic fields, allowing scientists to detect them through specialized experiments like the Axion Dark Matter Experiment, ADMX. Axions are also linked to quantum physics, as they could explain why the strong nuclear force behaves the way it does. If proven to exist, axions wouldn't just solve the dark matter mystery but could also answer fundamental questions about particle physics. 3. Primordial black holes. Dark matter as ancient cosmic relics. What if dark matter isn't made of particles at all? Some physicists propose that it could be composed of primordial black holes, tiny black holes that formed shortly after the Big Bang. Unlike the black holes formed from collapsing stars, these could be much smaller, ranging from the mass of a mountain to several times the mass of the sun. Primordial black holes would exert gravitational effects similar to dark matter, but so far, searches for them have come up empty. However, recent observations of gravitational waves have reignited interest in this theory. 4. Modified gravity, a radical alternative. What if dark matter doesn't exist at all? Some scientists argue that instead of searching for an invisible mass, we should rethink our understanding of gravity itself. Modified Newtonian dynamics, MOND, and other alternative gravity theories suggest that what we perceive as dark matter might actually be a flaw in Einstein's equations at cosmic scales. While MOND can explain some galactic observations, it struggles to account for large-scale structures like galaxy clusters. So far, no modified gravity theory has successfully replaced the need for dark matter, but the idea remains an open question in physics. If dark matter is out there, how do we find something that doesn't emit light, doesn't reflect it, and barely interacts with the world around us? Scientists are using some of the most advanced experiments in human history to detect its presence, deep underground in outer space and even inside massive particle accelerators. Let's explore the main methods researchers are using to uncover this cosmic mystery. 1. Underground detectors, waiting for a whisper. Since dark matter doesn't interact with light, scientists are searching for it in total darkness. In deep underground laboratories, massive tanks filled with ultra-pure liquid xenon or argon are waiting for a tiny, rare interaction, an elusive dark matter particle colliding with an atomic nucleus. Experiments like Xenont in Italy and Lux Zeppelin in the US are designed to capture these fleeting interactions. These detectors are placed underground to shield them from cosmic radiation, which could otherwise create false signals. So far, no definitive dark matter particles have been found, but each upgrade makes these experiments more sensitive than ever before. 2. Space-based observations, looking for clues in the cosmos. If dark matter can't be seen, perhaps its gravitational effects can. Astronomers use space telescopes like Hubble, Chandra, and the James Webb Space Telescope to study how dark matter bends light around galaxies, a phenomenon called gravitational lensing. By mapping these distortions, scientists can estimate how much dark matter is present and how it's distributed throughout the universe. One of the most stunning examples of this technique comes from the Bullet Cluster, where 2 galaxy clusters collided, leaving a visible separation between normal matter and the invisible mass thought to be dark matter. Another space-based method involves detecting high-energy cosmic rays, which could be a byproduct of dark matter particles annihilating each other. The Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station is scanning for these signals right now. 3. Particle colliders, creating dark matter in the lab. What if we could manufacture dark matter instead of waiting for it to appear? That's the goal of high-energy particle colliders like the Large Hadron Collider LHC at CERN. By smashing protons together at nearly the speed of light, physicists hope to generate new undiscovered particles, possibly WIMPs or axions. One strategy is to search for missing energy in particle collisions. If dark matter is created, it might slip away undetected, leaving an energy imbalance that scientists can measure. While no dark matter particles have been produced yet, each experiment refines our understanding of what we're looking for. 4. The search for axions, tuning into a cosmic signal. Axions are thought to interact weakly with electromagnetic fields, which means they might subtly convert into photons under the right conditions. Scientists have built highly sensitive detectors, like the Axion Dark Matter Experiment, ADMX, that use powerful magnets to try to capture these conversions. It's like tuning a radio to an unknown frequency. Scientists systematically scan different energy ranges, hoping to pick up a signal. If axions exist, they could be the key to solving not just dark matter, but other mysteries of fundamental physics. With all these methods working in parallel, the search for dark matter is one of the most ambitious scientific endeavors of our time. But after decades of searching, what happens if we still don't find it? Could dark matter be something even stranger than we ever imagined? Dark matter is one of the biggest unsolved mysteries of science. If we discover its true nature, it could redefine our place in the universe. Whether it's made of exotic particles, microscopic black holes, or something even more bizarre, the journey to find it is leading us toward the next great scientific revolution. What do you think dark matter is? Let us know in the comments, and if you enjoyed this, subscribe for more mind-blowing science.